Hello everybody, welcome back to another business calculus video. In this video, we will be talking about exponential functions. So, thus far, most of the mathematics we've done has been with polynomials. And polynomials tend to grow at relatively slow rates, right? So, for instance, if we let f of x equal x squared, then f of 5 is equal to 25. F of 12 is 144. And f of 30 would be just 9,000. In the language of derivatives, right, f prime of x is 2x, a linear function. And linear functions grow at a constant rate. So f(x) is never really, its growth is never really spiraling out of control. But what if we just swapped the role of the exponent and the base? So the exponent and the base. What if we swap those? And we said, let g of x equal 2 to the x power. So now we have, instead of a variable base and a fixed exponent, a fixed base and a variable exponent. Let's try testing those same inputs and see what we get. Well, g of 5 is 2 to the 5th power, which is 32. G of 12 is 2 to the 12th power, which is 4,096. Oh, I'm sorry. This should not be. No, it is 32, right? Yes. Cool. My math's bad. All right. And then finally, g of 30 is, let's see here, making sure I get this right. 1, 2, 3, 4, 5, 6, 7, 9. 1,741,824. So, in my professional opinion, trained by many long years of math, I'd say this function grows just a little bit faster than that one. And that's the power of an exponential function, is it models kind of fast growth. So things like bacteria replication that happen very quickly get well modeled by exponential functions. So, here's our definition. The exponential function with base a also, the notation I use might be slightly different than your book, but I enjoy teaching it this way, so we're going to do it that way. So, the exponential function with base a is defined for all real numbers, so all x in R, by f of x is equal to a to the x power. Okay, makes sense. Exponential function with base a is your base, x is your exponent. And we're specifically going to only work with values of a greater than 0. Why is that? Well, because if we want to be working with all x in R, maybe I want to work with x equals 1/2. And square root of 1/2 makes sense, but, a square root of a positive number makes sense, but maybe a square root of a negative doesn't. Or if you put a negative sign in a, right, it'll start bouncing back and forth. They'll basically make it a very unwell-behaved function. So we're going to stick to positive a. All right. Note that when a is equal to 1, f of x is 1 to the x power, which is just 1. So, we have a fast-growing function whenever a is not 1. Whenever a is 1, we're just going to get a constant function. Okay, So, as I said, these naturally come up in population dynamics, and this actually is a very natural function in economics. Also, quick note, your book says this explicitly, but all of your standard exponent laws still apply. So if you're working like a to the x times a to the y, that is still equal to a to the x plus y, and that's true for every choice of real number, x and y. So that's nice. Alrighty, moving forward. We should probably get some practice graphing a couple of these. Let's maybe graph x squared, or not x squared. Let's graph 2 to the x and 1/2 to the x. See what happens. Alright, so let's do it by a table, since we don't really have any other way at this moment. So we have f of x equal 2 to the x, and g of x equal 1/2 to the x power, which we'll note is 2 to the negative x power. Alright, so some test values for x. Let's just do -3 to 3. Okay, 2 to the negative third power is 1 over 2 to the third power, okay, 1/8. 2 to the negative second power is 1 over 2 to the second power, so 1/4. Similarly, we'll get 1/2 there. 2 to the 0th power, just 1. Anything to the 0th power is 1, with the possible exception of 0. 2 to the first is 2, 2 squared is 4, and 2 cubed is 8. Alright, so those are our values for f of x filled out. Now let's do g of x. So, 1/2 to the x, which is the same as 2 to the negative x by our laws of exponents. So, -3, g of -3 is 2 to the -3, so 2 to the positive 3, 8. So our table will fill out as 8. Similarly, g of -2 will be 4, -1 will be 2, 0, 1/2, 1/4, and 1/8. So it's almost like these are just mirrors of each other, right? Across that, sorry, that should be a 1. Across that middle line of 1, right? They're mirrors. So that's cool. Okay, let's actually graph each of these and see what that looks like. Alright, so let's make our x-axis have scale of 1. And I'll make my y-axis have a scale of 2, just for the sake of it. So 2, 4, 6, 8. Alright, if we graph these, let's do f of x in red. We'll have the point -3, 1/8, so right over there. -2, 1/4. -1, 1/2. 0, 1. 1, 2, 2, 4, and 3, 8. So even with a scaled down y-axis, you see that this function is growing very, very quickly. Now let's graph, so that's our graph of f of x, right there. Now let's graph g of x, and let's do that one in blue. Again, plotting those points, we'll have -8, or +8, 4, 2, 1, 1/2, 1/4, and 1/8. So, connecting the dots, we see that the graph of g of x looks roughly like this. For those of you who remember transformation of functions from a pre-calculus course, you'll recognize, hey, because we put a negative x in for the x in f of x, that's the same as flipping the function across the y-axis, and that's exactly what's happened here. F of x and g of x are mirrors across that y-axis. That's nifty. Alright, so let's list out some basic properties of exponential functions. I'll erase down here since it wasn't really relevant for our graph. So, for any a greater than 0, a to the 0th is equal to 1. So 0, 1 is on the graph of any exponential function. The point 0, 1. So as long as you don't do anything weird to the function, if you're just working with something of the form a to the x, no matter what a is, it always will pass through that point. That's kind of a nifty fact. Another one, the general shape of these functions is completely dependent on your value for a. If a is greater than 1, the function grows as x does. So kind of like f of x, it's going to grow as x does. If a is between 0, 1, the function shrinks as x grows. And we again see that with the graph of g of x. And we've already talked about the case where a is equal to 1. That's just the constant function at 1. Alright, what are some other properties of exponential functions? Alright, let's see, in either case, this a greater than 0 or a less than 0, the x-axis will be the horizontal asymptote. So in other words, the limit as x goes to infinity of a to the x is equal to the limit as x goes to negative infinity of a to the x, and they're both 0. No matter what the value of a is. We see that here. Or sorry, I guess I should say, that's not a quite true statement. This limit is 0 for a less than 1, and then the negative infinity 1 is for a greater than 1. Yes. That's on me. Okay. So, why is that? Well, because if we have a number less than 1, then as it gets multiplied with itself over and over again, that number keeps getting smaller and smaller and smaller. Therefore, the limit as x goes to positive infinity of a to the x is 0 when a is less than 1. But when a is greater than 1, okay, then you need to be working with negative powers. So it'll be 1 over a number multiplied by itself again and again and again. That's getting bigger, so the overall fraction is getting smaller, which means it goes to 0. And it's pretty clear on the graph, right? This is the general shape of the exponential function, so hopefully you're able to see both of those things pretty easily. Okay, what are some other properties? Let's hear. Oh yes. Let's let f of x equal a to the x with no restriction on what a is, as long as a is greater than 0. Then the domain of this function is all real numbers. This exponent is always going to be defined. The range of the function is open interval 0 to infinity. So we can get all positive numbers, not 0. It limits to 0, but it never equals 0. And f of x is continuous, even differentiable. Alright, so we have a very nice function when it comes to the exponential function. Let's do some more discussion. Namely, why do we care about it? What the heck is it even good for? So your book puts this discussion off until section 5.3 on compound interest. We're going to handle half of it now and half of it later, just because I think it's better to see, okay, why do we actually care about exponential functions, rather than for me to give you like, oh yeah, here's how they work, and you have no reason to care about them. So let's talk about why you should care about them. Alright, so compound interest. And let's call this part 1. Alright, let's say we start with some amount of money and we're trying to invest it. And let's say we're investing it at an interest rate, or a I guess I'll try to use your book's vocabulary, even if I don't use their notation, a nominal interest rate R per time period t. Alright, so typically t will be like measured in years in some way, shape, or form. So, for example, a principal is how you say it. And yes, you spell it like principal school official, not principal the moral code. So we have a principal, $4,000 into an account with 8% interest per year. And the natural question becomes, okay, well, how much money is in my account after a certain amount of time? All right. Let's call the value of the account, aka the amount of money in it, A of t, right? So the amount of money is going to be a function of the amount of time you spent investing that money. So, what is a good formula for A of t? Well, let's try to figure it out. Before any time passes, we have what we put in, right? We have the principal for the account, because that's what we're starting with. In other words, A of 0 is equal to P. Okay. Let's say my first time period passes. What would A of 1 be? Well, I still have the money I started with, plus I get some interest, right? How much interest do I get? Well, I have my interest rate times however much money was in the account at the previous time period. So A of 1 is P plus P times R, which I'm going to factor out as P times 1 plus R. Okay, what about the second time period? A of 2 will be this amount of money, the amount of money I had in the account, plus whatever interest I got. So it would be P times 1 plus R plus P times 1 plus R times R. If you factor the P times 1 plus R, that times 1 plus R. Or in other words, P times 1 plus R squared. And this process would continue. Every time it compounded, you would just add another factor of 1 plus R. That's how compound interest works. So it turns out that this is an exponential function. In general, A of k would be equal to P times 1 plus R to the k. So after k compoundings, this is how much money we have in the account. So if you, like me, had older relatives that would come to your dinner table on Thanksgiving or Christmas and be like, oh, compound interest, it's so good, you should invest early because it's compound interest. As much as I hate to agree with anybody over the age of 50 on anything, they are completely right. Compound interest is very powerful because we've seen how fast exponential functions grow already. And if we're working with an exponential function, well, it's going to grow very, very fast. And that's why banks keep interest rates, these R's, so low. Because if the interest rate were any higher, then this number would be big enough that it would start multiplying out of control ridiculously fast. So they keep that number low. Of course, y'all are business majors, so y'all probably already knew that. Okay, so where do we go from here? Well, we go to my next page of notes, that's where we go. All right, so now, let's say that maybe our money doesn't compound just once per year. Maybe our money compounds twice a year, or maybe once a financial quarter, maybe once a month, maybe once a day. How do we account for that with our formula? Well, we're going to make a slight alteration. So this would be compounding once, but we want a general formula that can handle compounding as many times as we have set up our account to do so. So let's say that our account compounded m times per time period instead of just once. Then the question becomes, okay, how much money do we get per compounding? Our new interest rate would be R divided by M. Okay, why that? Why does that make sense? Well, if I'm supposed to get R as my percent interest rate, right, per time period, and now I'm compounding, let's say I'm compounding 3 times over the course of the time period, then my R gets spread out, right? It gets spread out to the first chunk, the second chunk, and the third chunk. So we get R divided by M as our new interest rate per compounding period. And our new let me rephrase that as we have M times T new time periods. Right? So if I'm compounding 3 times per year, then over the course of 1 year I'd have 3 times 1 new time periods. And my interest rate for each of those would be my original interest rate divided by 3. So now our formula becomes A of t is equal to P times 1 plus R divided by M to the MT, where R is going to be the nominal interest rate M is the number of compoundings in a given time period. So if this were like quarterly, M would be 4. If this were daily, quarterly, our time periods were years. If our time period was a year and M was daily, then M would be 365. P is still our principal. A is the amounts in the account, and then T is the number of time periods that have passed. Hopefully that is all legible. Alright, so this is our new and improved formula for compound interest. This is one to remember, especially for people who want to go into the business world. This formula becomes very important. So let's do an example of it. In fact, let's go back to our original example. $4,000 invested into an 8% interest rate per year account. Alright, so we have this setup, right? And let's see what A of 3 and A of 7 So the amount of money in the account after 3 years and after 7 years, if the account is compounded at various different rates. So if interest is compounded annually, semi-annually, twice a year, quarterly, monthly, and daily. So in other words, we're handling the cases M is equal to 1, 2, semi-annually, 4 is quarterly, 12 for monthly, and 365. So this is the formula we're going to be using. I'll write it up there and we'll start referencing it. your general formula is A of t is equal to p times 1 plus r divided by m to the mt power. Grab some new chalk. For our specific case, since we're working with the same account being compounded at various different rates, let's make life easier on ourselves. Let's give this new notation a sub m of t to be our account setup, but leaving m as a variable. So it'll be $4,000, our principal, times 1 plus our interest rate, our nominal interest rate r, so 0.088%, divided by m to the mt power. So we want a sub 1 of 3, a sub 2 of 3, a sub 4 of 3, yada yada yada, and then the same for 7. So let's compute those. A sub 1 of 3. So this is our account after 3 years if it's being compounded annually. A sub 1 of 3 will be $4,000 times 1 plus 0.08 divided by 1 to the 1 times 3. Which, if you grab that, you would need a calculator for this. Put that into a calculator, you'd get $5,038.85, roughly. Okay, how about a sub 2 of 3? Well then, a sub 2 of 3 would be $4,000 times 1 plus 0.08 divided by 2. Now we're working with m being 2 to the 2 times 3. So now we're working with 4,000 times 1.04 to the 6th power, which would be, if you plug that into your calculator, roughly $5,061.28. So we see that increasing the amount of times that we compound has increased the amount of money we make. What if we skip 4 and 12? Let's just jump to 365. Your exercise, compute a sub 4 of 3 and a sub 12 of 3. Now let's say we are compounding daily. A sub 365 of 3 would be, according to the same formula, $4,000 times 1 plus 0.08 divided by 365 to the 365 times 3 power. So a very large power. Plug that into your calculator and you'd get roughly $5,084.86. Okay, so with an interest rate of 8%, over the course of just 3 years, we made, depending on our compounding, somewhere between $5,000 and $5,084, right? So $1,000 more than what we started with. Now, obviously, your bank account doesn't grow that fast. Why? Because your interest rate is not 8%. Your interest rate is probably something like 2 or 3%, and that slows down growth substantially. Yeah, this is why college loans also sound like such a great idea up until the moment they come collect, because interest rates mean a lot. Ditto with credit card debt. Alright, I said we should also do it for A of 7. Let's do a couple of those. In fact, let's do the same 3, and then as your exercise, you can also do a 4 of 7 and a 12 of 7. All right. A 1 of 7 would be $4,000 times 1 plus 0.08 divided by 1. Now, instead of being to the 1 times 3, it'll be 1 times 7, since we're working with t equals 7 now. And that would be roughly $6,855.30. A 2 of 7 would be $4,000 times 1 plus 0.08 divided by 2 to the 2 times 7 power. So we're working with 1.04 to the 14th power. That'll be roughly $6,926.71. As I said, a 4 of 7 exercise, a 12 of 7 ditto. Let's do a 365 though. A sub 365 of 7 will be $4,000 times 1 plus 0.08 divided by 365 to the 365 times 7 power, and that would be roughly $7,002.26. So we see that the difference between annual compounding and daily compounding only was a difference of, I don't know, like $46 roughly, $46.01 when we're working at 3 years. But if you go and look over at the 7-year marker, now you're having a difference of $147. So the difference in compounding rates, well, compounds as time goes on further and further. So if you can secure a good account with a high compounding rate and you let it grow for a long time, it makes a bigger and bigger difference the longer you let it go. All right. So let's look kind of closely at this function, right? This p in the front, like it's cool and all, but it's really just a scaling factor. It's just multiplying everything. Okay. So it seems like the real grunt work of the function is in this part, the 1 plus r over m to the mt power. Let's look at that a little bit closer. What happens if instead of compounding at a fixed amount of times, I start compounding faster and faster and faster? Basically, what would happen if m gets really, really large? In other words, what happens if we take a limit as m goes to infinity of our compound interest formula? So it turns out that as a function, the limit as m goes to infinity of 1 plus 1 divided by m to the mth power. Well, you'd say, okay, well, it's something to the infinitieth power. Shouldn't that be going to infinity? Well, if a number is bigger than 1. But 1 over m is going to 0. So this number is going to 1, and this power is going to infinity. And turns out the rates of that happen kind of balance each other out. And this limit ends up being a new number called e. And e is going to be our most special choice of base for the exponential function, because it even further turns out that the limit as m goes to infinity of 1 plus x divided by m to the nth power is e to the x. But this is very close to our formula for compound interest if the compounding was to happen almost at every instant, continuously. So, that's why this function is going to be important. First, let's define it. The natural exponential function if you ever hear me say the exponential function, this is the one I'm talking about, unless there's another specific one that's clear from context. Is f of x equal to e to the x? Special enough that your calculator has a button for it. So, pretty dang special in my mind. Let me grab more chalk. And yeah, this single function is probably the most useful function in all of mathematics. It has applications in physics, computer science, biology, economics, other areas of math. We're taking a calculus course now, but you can do calculus with complex numbers, and it's known as complex analysis. E to the x is the single most important function in complex analysis. Yeah, basically, you get a lot of work out of this little function, which is weird because it's just a limit, right? Later on, we'll see that e to the x has a cool property with its derivative that'll make it so useful, but we'll get to that. Where were we? It's continuously compounding interest. The main thing that we will be using it for. So, let's take the limit of our compound interest formula as m goes to infinity. The limit as n goes to infinity of p times 1 plus r over m to the mt, by our limit laws, p comes out, and this is equal to p times the limit as m goes to infinity of 1 plus r over m the mt, which we've said that if we just had x instead of r, it would go to e to the x. So this is equal to p times e to the rt. Why? Maybe another step would be helpful. This is p times the limit as m goes to infinity of 1 plus r over m to the m, all that to the t power, right? By our rules of exponents, this is to the m to the t power, and laws of limits say, oh, you can pull that out. So now, hopefully it's more clear. This is p e to the r t. And this will be our formula for continuously compounded interest. So for example, let's find the amount after 6 years if $2,500 is invested at an interest rate of 15% per year. So a ridiculously exorbitant interest rate. but one that makes our numbers work slightly nicer. So that's why I'll choose it. Oh, and let's say it's compounded continuously. So again, continuous compounding is when you're saying, okay, we're compounding every instant, we're letting m go to infinity. Well then in this case, a of 6 would be equal to, by our formula, $2,500 times e to the 0.15, that's our r, times 6. Do the multiplication, it's $2,500 times e to the 0.9 power. Plug that into your calculator, and that would be roughly $6,149.01. Alright, so your book has a bunch more examples of these. Hopefully it wouldn't be too hard to go from this example to all of those. All the theory is the same. The main thing to remember is your discrete interest formula. So we have the discrete one, which is a of t is equal to p times 1 plus r divided by m to the mt power. So this is if you're compounding m times. And then we have the continuous compounding formula, which is a of t is equal to p times e to the rt. Alright, so that I think wraps it up for our study of exponential functions, or at least the setup for exponential functions, and half of the discussion of compound interest. I'll see you all in the next video.